First cart exploration. This is something that's going to go in your binder. So this is going to be stamped at some point. You're going to add to this as you explore today, and periodically I'll be asking you questions that you can reflect on. Okay, I'd like you to get where you can see this setup. Can you see this cart? Actually, let's have these three people move to a different spot. You guys mind? So we're going to have this cart and track system, which you're familiar with. And we're going to think about the motion of this cart. Everybody see okay? All right, so I have this cart, and I'm going to let it move on this track. What I'd like you to do is to describe the motion of this cart on this track as it goes along this track. And I'd like you to tell someone sitting next to you what you think the motion, how the motion is described. A couple seconds to do that. Okay, what do you think? Trey, what kind of motion is it?
Constant, like, would it be negative velocity because it's going down?
Constant negative velocity, it's going down. It's not really going this way down. What do you mean by down?
Down because it's a slope. Down.
Okay.
Or
So
it'd be positive. I don't know. I'm not sure.
how would we decide if that was positive or negative? You hear his dilemma. He's saying, "Okay, I want to describe this well. What do we need to do to kind of sort that out?" This side where the start is, where you're starting from. So if I start here and I call this direction negative, then Trey's description is exactly right. If I called that direction positive, then it would be positive constant velocity. For the sake of simplicity, we're going to call that positive, but we will have a negative velocity. Okay, so we're going to say this way is positive. So now what happens? Talk about what happens here. Turn to somebody at your table and talk about what happens with that. Okay, what are some things we can describe? And let's stick with the motion. Let's stick with the motion. What happens to the motion of the cart? Okay. The motion changes. Constant, listen to what Justin's saying. Constant positive, then constant negative. Okay, so you agree with that? Constant positive, then constant negative. What about if we could isolate this part right here? What do you think is happening here?
Stop.
It's stopping, and it's turning around then, isn't it? So is there another way to describe, besides constant positive and constant negative, which is a very nice description of that, is there any way to describe what happens right here in this interaction? It does reverse direction, good. What about motion? What about the motion? It's not constant positive or constant negative, is it? Trey, what do you think?
The spring actually takes some of the energy away from the force going backwards.
Okay, so we're throwing energy and force in there. Those are big concepts, aren't they? Let's think about if it's not constant positive or constant negative, what do we call motion that's not constant?
Accelerated.
Accelerated, isn't it? It's accelerated motion. Do you agree with that? Okay, so we have constant positive, constant negative, and here we have acceleration. Tell me some things we can measure now about the system. Now we're going to go a little bit more complex. And I do have detectors here. This one says dual range force sensor on the top, and this is a motion sensor. So what are some things that I can measure about this whole system if I set this up like this? What are some things I can measure? And I'd like you to come up with at least 3 with your table. 3 things that you can measure about that system. Anybody dying to use one of those really good?
I will.
Everyone do it.
No, I will.
Try and have her hands up. Thank you. You want to
You
help?
get it next time. I'll do it next time.
Okay. So what are some things you could measure about the system? Give me one from your table.
The speed as it's going towards the force essentially.
Okay, so the speed, what do you want to call that? The first speed or incoming speed? Positive speed. So you can measure the positive speed. Let's have something else. Okay, the acceleration. They're saying you can measure the acceleration. Good. What about over here? Shelby, your table. Anybody from your table? What else could you measure?
Time.
Time. Okay. What time would you measure? The time for the whole thing, the time for the interaction?
The whole thing.
Okay, you can measure the whole time. Is there another time that you can measure?
Recoil.
The recoil time. So we could measure that time right here, couldn't we, for turnaround? So why don't we put the recoil time? The recoil time also. So you can measure the entire time or the recoil time. I like that. The way to call that. Recoil is RECOIL. All right. What else could you measure? What about over here? What?
Mass of the car.
The mass of the cart. You certainly could. You could just take the cart and take the mass of it, couldn't you?
Yes.
Okay. Anything else?
Distance.
Distance. Good. Distance. What else?
Length of the track, how much?
Length of the track. Anything else? What? Given our sensor here.
Force acting.
Yeah, you bet. We want to think about measuring the force because you've used that force sensor before. That will measure that force during the interaction, won't it? Okay, let's think about the measurements that we have on the board. Thank you. Let's give Triangle one clap for doing such a nice job. 1, 2, 3. Great. So we've got the mass of the car, the recoil time, the positive velocity. We didn't get the negative velocity on there, did we? The distance and the force. We're going to pick out a few of those to look at. We're going to pick out 4 of those to be exact. Here's what I'd like you to look at. I would like you to look at the mass of the car, the positive and the negative velocity. And the recoil time and the force. The distance is actually in the velocity, isn't it? It's already included, right? That comes from that,
The speed and distance.
pardon me?
You come from the speed and the distance.
Right, it comes from the speed formula, distance per time, right? All right, so here's what we'd like you to do. We have 8 setups around the room, and we would like you to take a look at, with the Lab Pro software, the mass of the cart times the change of velocity. We would like you to figure out what that value is, and this we would like you to average a number of trials. It looks like it's divided by the average. So the mass and the change of velocity, and we want you to compare that with the force times the time of interaction. And we would like you to compare those 2 numbers. All right? So the mass of your cart times the change in velocity will give you a value. And the force times the time of interaction will give you a value. And here's what we'd like you to do. As you do the first measurements, we want to give you an okay to go on, because we want to make sure that you're looking at the graphs correctly. you're gonna be looking at log or pro graphs. One either give the, yep, you can go on, or let's reconsider. Question?
What's the max times the positive and positive each trial? Or the average?
The average of a bunch of them, but it's the change in velocity. So it's the first velocity and the second velocity, the difference between those two. Yep. Do you understand Justin's question? This change in velocity is v final minus v initial. It's the difference. It's the difference in those two velocities. All right? 7, 8, 9. Yeah, we're going to have groups of 4, I think. 8. Yeah, we're going to number off. Okay, so this is the system that you're going to have plus a computer. And those are set up around the room, and we'll kind of sort those out for you and get you directed where you're supposed to be. One thing that Miss V and I found out when we did this the other day, you're going to get the best results if the motion detector is close. And if that interaction happens close to the motion detector. Well, it's just, we just found, we were kind of confused a little bit, honestly. We tried a whole bunch of different setups, and we tried one with the detector way back here, and the best one that we found was just here. And we also taped a card on so that the motion detector could see, so it could bounce off that surface of the card. Also, you want to make sure that this is a clean interaction on this side. Okay? That it's hitting. What I mean by clean is that it doesn't deflect off. You want the force all transferred to the sensor. Okay, so tell me with the fist of 5, if I need to go over some more stuff or re-clarify, that's a 0, you don't know what you're doing, or 5 if you're like, yep, I know what I'm supposed to be doing. So just give me a little bit of feedback. Okay, we'll be seeing a few people then. All right. How hard you push the cart? It's really not going to matter, but you don't want to overdo it so you break anything. You know, I mean, you can push it that hard. Oh, another thing that we want to do is anchor down the ring stand. There are big weights that we'll have out. You want to make sure that this doesn't move. Because, see that? I mean, that's just a little bit of a... Good. Will the velocities be different? They could be. They could be. We want to see if that interaction, I really like that question. If there's a way that you could say, all right, we're always going to push it the same, you could, but we're more likely looking at these interactions for matching pairs. Okay? Because if you do a whole bunch of averages, okay, I'm going to rewind on that. You know how I asked you to do the average of a bunch? What we'd like you to do is a bunch of pairs. Okay? And that'll be clear as you get to your software, as you look at your data interpretation. Instead of taking 10 and just averaging them, what we want you to look at is a number of different pairs. Okay. So we're going to number off, and you're going to be in group 1 through 8. We'll start here 1 around the room to 8 on the other side. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Okay, if there's somebody in your group that you don't know, introduce yourself as you go. We will start with the 1 group on this side. Who's captain of the 1s? Kenzie? Who's captain of the 1s, the 2s, the 3s, the 4, 5, 6, 3, 7, 7, and 8. So those are going to be the captains of the groups. Okay, so that's where you're going to go to. Can you challenge them?
Yeah.
To be captain?
Yes.
I suppose. I don't know how that in my head I'm thinking, how is that going to work out? All right, go for it. Each captain
F initial. What F initial is 0?
Is it 0 there?
You're looking at one force. You're looking at this force.
The force that it hits the thing at, right?
That's right.
Alright.
So you should be able to read that force off your graph.
Yeah, but we're talking about velocity though.
Okay.
How do you know how to find the change in velocity?
Why is it
So the
negative?
motion detector would show you velocity, wouldn't it?
Mm-hmm.
And then the force would show you the force. And the force detector would show you the time in that direction too, wouldn't it?
Yes. So will we multiply? Alright.
One's
I'm
a
gonna do a
negative
run.
force.
It's
I'm gonna do a
Okay.
run and then.
Okay. Velocity or force? Force. Okay. So that means that a negative force would correspond to pushing or pulling.
Alright. So
negative
force is
all.
a negative force. Negative force would be pushing it.
Okay. So a negative force would be pushing. And if I pull on that, what should happen? Is it showing that?
No, I already collected a run just now.
Does that make sense, Trey? If it can be negative, it's sort of like we said, if that direction's positive, that direction's negative. This push is showing negative, and the pull would be positive.
Remember when we did the graphs for a position and moving away from the origin was positive, moving towards the origin was negative?
If it picks it up without a piece of paper, you're fine. Yep.
and then why is it still
I'm gonna answer this one then.
What, the force?
So what are we doing?
A lot of nut.
Yep, you gotta readjust, don't you?
Yeah.
Okay, question, shall we?
Is this right?
What part? You tell me.
Well, we're just collecting data, I guess.
Okay, so can you tell me what's happening with those on the red peaks? What's happening there?
That's hitting that's the coil.
Okay, can you tell me the maximum force on that? Could you read the maximum force on that?
Would it be
Good, and then could you tell me how long it took to do the interaction?
more than 7 seconds?
Okay, so wouldn't that be on this axis?
Yeah.
Yeah, and I'm gonna show you a way to get that.
This time that she's talking about is like not even 10.
I'm gonna show you that. It's just the time that it's bumping into the system.
Oh, that's it?
Yeah.
So that would be.
She doesn't. So,
So we changed the course?
It's not looking up.
Ready?
yeah.
Oh, yeah, do another try. Ready?
Are we still doing that?
Well, you gotta keep going.
Our mass is constant, our velocity is zero.
You leave everything exactly where it is, but you have to log off your computer. So when you come back next time, we'll take a look. Last time you kind of got to start with the lab equipment.
Yes.
What were we looking at? Tell somebody sitting next to you what we were looking at. What were we measuring? What were we supposed to be comparing? Talk about that for a few minutes. No, not for a few minutes. 30 seconds. Go. Okay. Okay. Good. Just an organizational reminder. You're free to take notes on this because this is going to be a binder check tab. So you had a notes sheet started. Anything from this discussion would be applicable there. All right. So what were we looking at? I'll give you one thing, Sam. What were we looking at in this situation? Okay, we were looking at the recoil, weren't we? So the recoil, that something was happening there to change its direction. And what were we measuring? What were we measuring? Okay, we were looking at the force of the impact, right here, by the force sensor. What else?
The velocity before and after.
Good, the velocity before coming in, and the velocity after. What other thing do we measure? Two other things we measured. I'll come back to you. Louis? Yeah, positive, negative velocity. What else about the cart? Show me. The recoil time, the time of that interaction there. We were like, okay, it's hitting the sensor and it turned around. We want how long that happens, don't we? And what else do we measure about the cart? Corey, it's mass. Yes, it's mass. Very nice. All right, here's what we want to look at. Now that you've had a chance to take a look at what kind of data you get, I want to show you specifically what to look for on the Logger Pro screen. So, and before we do that, I want you to make a prediction. Can everybody draw this graph for me? Make a V versus T like this. Make a V versus T. And make a prediction as to what this V versus T graph looks like for this action right here. Coming in, bouncing off. What does that V versus T look like? What does it look like? Compare with a neighbor. Once you've made your prediction, take a look and see if you agree.
You forgot to do this? You did opposition.
Constant positive velocity. Very nice. So how do we show that here? Good. And then what happens when it turns around? What kind of velocity is it? After it's turned around. You want to see it again? All right, let's take a look at this. I'm going to pick on Daisy a little bit. I said, what kind of velocity does it have coming in? And she wasn't sure at first, but then she said it's constant positive velocity. She remembered that from the first motion unit. So then, how do we know to draw that? It's a straight line. Okay? I want to pick on somebody else. What happens then, or what kind of motion is it when it comes off of there? Not during this, but after. What do you think, Jose? A negative constant velocity. If this way is positive, then this way is negative, isn't it? But what do I do in between there? What happens here? Does that take any time? It does, doesn't it? That's the time that we were looking at when we talked about it. Was it Shelby that said the recoil time, maybe? Yeah, the recoil time. That's the time that we're looking at. So what about the force and time graph? What do you think the force and time? So you got the force sensor on the right over there by Jordan. And you have force. And you have time. What do you think is happening with the force sensor right now? Nothing. Nothing, 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 then what? Boom. Right? And then what? Something or nothing? Nothing.
Nothing.
Nothing. So we got nothing, 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 boom, and nothing. Can we turn that into a graph?
Yeah.
What do we do? Straight on the line. Nothing, 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 and then we know it does nothing, 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 nothing later. What does the boom look like?
Oh, so V.
Oh, okay.
So the V goes
We got a
down.
V. All right. How do you know it goes down? Did you see that in the?
Because like on motion graphs, when you're going towards the origin, it's negative. When you're away from it, it's positive.
Okay.
So the little lever thing is like you're going push it in, you're going towards the origin.
Okay.
Pull it out. Going away.
So pushing into this sensor is negative. I'll tell you that. So if I pulled on it, it would be positive, a positive spike. So we've got a negative spike right here. Okay. So here's what we want to do with the analysis. And you guys all kind of explored this a little bit already, but I want to show you some specific things about what you do with it. On my graph, I have this spike right here. And I'm going to highlight it. I'm going to highlight just the spiked part. And then I'm going to do the integral. See this button right here? Everybody see that? It's kind of small. That's the integral. You're going to do that for the spiked part. And that's going to represent our force times time, right here. When you get the integral, when you do the integral now, we've got some pre-calc people that can say, yeah, I know what that actually means. What does that mean when you take the integral of something? Well, you're about to learn it. When you do the integral, let's say you have a line like this, and you want to take the integral. You're basically finding the area under the curve in little bits of little areas, okay? So what you're doing with this graph is you're finding this area, which would be a product of the force and the time, just in little slices, okay? So that's how you're going to get this value. You were in the process of getting force time values. You're going to use the integral, now that you've explored that. The other one that you're supposed to compare over here was MV, M delta V. You know how to do the mass. The mass is just take the mass on the scale. How are you going to get the delta V if you look at this? If you look at this graph right here, how can I tell what the delta V is? Okay, I can take the average, and my average would probably be, if I have a high and a low, would my average be 0? What's the formula for change in velocity?
It's,
What do we have up here?
is that the V equals radical? Oh no, VF minus VI. Oh yeah, sorry.
It's all right.
Oh, poor me.
You were doing FC, I think. Okay, so when we look at the change in velocity, we just take the final velocity minus the initial velocity. Can we get the final velocity from here? Yep, you're going to do the examine button, and you're going to go, what is the velocity right there? And you're going to say, you remember using the x equals button before? Up here? It just lets you take any point and figure out what it is. So you're going to take the final velocity minus the initial velocity, and you want to get it as close to that interaction as possible. See how it's right here and right here. F of V minus, or VF minus VI will be delta V. You know how to get all of these now?
Yes.
And what are we doing?
Compare.
Comparing. What does that mean?
Comparing.
Are they inverse? Are they opposite? Are they one's a square of the other? Are they the same? That's what you're exploring. We want to get this on whiteboards today. So as efficiently as you can. Did we have a setup, Ms. V, that did not work, or did we get them all working? Is this one not working?
That one, the computer wasn't working yesterday on that one, but I don't know if it is today or not.
Okay. So who was at that station where you trained?
The far right one?
Yeah.
All right.
Okay, so we'll work with you guys to make sure that works. Okay, any questions on what to do? All right, let's go.
Oh, we better, because all these were correct, it's just that we had just like straight lines.
It wasn't zoomed in enough? Yeah.
Did we get it?
Got it.
Hey, how do you know you got it? To match the motion?
Yes.
Yeah, good. So what about the top one looks like it matches. The bottom one doesn't look very dramatic. What about, what do you think you can do to that graph to make it more readable? Good linearize, that's a good suggestion. What's my scale on the one that I have on the board?
Push harder. Where does it show it?
Okay, with the bottom.
No, here, let me see where it's at.
Right here.
The graph?
Yeah.
Forwards to time?
I mean, what are, see how the top number is 0.2? It's a 0.2? It's a really zoomed in graph, isn't it? What do you think would happen to your graph? That's about the same.
Zoom it in?
Right. So, you know,
Yeah.
you just change this top number to like 0.5 and the bottom number to negative 0.5. See what you get. You guys know how to scale that bottom graph too? You can go make this number 2, make that, or just do number 1, and then negative 1 as well. See what happens. Okay, that's good data. Nice work.
Don't tell her. This
So next, you highlighted the top, and you want to go to the integral graph. That's it. Yep. And that gives you an you guys both want to have that. And that's going to be, you know, the two things that we looked at, the FT and the M delta B. That's your FT. Okay.
We don't, where are the cards?
Great, can I keep repeating?
Next year?
Yeah, I'm gonna do, let's take a look at the boards. Generally, let's just look around the room. Is there a trend over here? Mackenzie, Ricky, Leo, Jordan, and Shelby? General trend here, what do you say? Any thoughts? What can you conclude? They look equal to me. I mean, as one goes up, the next one goes up, the next one goes up. I mean, they're not exactly equal down to the thousands place, are they? But they're changing and correlating the same. Okay, what about, oh, nice, Cart Corral. That even has a great name. And Tiger. Gabe, Corey, and Haley. What about your results?
Well, they're pretty closely related to some aspects of the change in time and the change in velocity. We had lost our times on there, so we had to go back and look at the graphs, and we only got a few of our graphs back, but
Okay.
they're pretty closely related if for the number for the change in velocity and the change in time. They're pretty closely.
Oh, the change in velocity and the change in time?
Yeah, with
How about the M delta V and the F delta T? Are those equal?
they're close to each other. They're not exactly
If
equal.
you use your imagination, some of them are pretty close. Some of them are not, though, are they?
Yes.
Some of them you might want to pitch out.
Yeah.
You would do, if you had the choice, more trials, I bet,
Yeah.
and save all your data.
Yes.
Great. Okay, what about, who do I have there? Jared and Brian? Brianna. Sorry, I couldn't read it. I thought it was Right.
Oh God, thanks.
My fault. What is what? Oh, that's a radiometer. You interested in that? We'll talk about it. Behind the board.
It's physics, dude.
Back here at this board over here, what do you think? Any, just a general summary of what you thought your results said?
Well, on the first one, it, like our times slowly increase, like our first velocity and all that, so what we thought it was gonna
Okay.
because as it increased, like they both increased.
So, did you hear what she said? As we look at one, the other one increases? And so you're thinking that there's a trend? Okay, that's excellent. What about back here? Jose and Justin?
Well, we think they're equal pretty much. When we found one, the other one was very close.
Okay, so they were actually, all of them were actually pretty close, weren't they? One of them you might want to repeat, but the rest of them, like the second one, that's a little off. But the rest of them were actually pretty close to being equal, aren't they? You could look at percent, what percent they are off, and do an analysis, a statistical analysis. What about this one? Mandy, Tia, Danny, Hannah, and Brian. What's the group? Any thoughts there?
Not really close.
Not really close, are they? You restart the lab and redo, maybe? If there was something that we could look at specifically. What about Louis and Trey?
They're pretty close, but we found out what we were doing wrong. We were putting in a goal before having it.
Oh.
So that's why the rest of our numbers are wrong. Right ones.
Okay, so you put the two up that you thought were valid in terms of how you did the
Yeah, the
integral?
top one not too close. The second one.
Second one is, yeah, pretty close. All right, and anybody in statistics? There's a way to statistically decide how close. Anybody in there?
Yeah.
We doing standard deviation, stuff like that? If we have a big enough sample, you can say what is close, right?
Our formula is radical sigma A plus sigma B.
Nice. Nice, good application. All right, how about the last board?
Not very close.
Not very close? They kind of jump around a little, don't they?
Whoa!
So you would, okay, wait. Be kind. So you would probably repeat and take more data too, I bet. What we're looking at is most of the data is saying that M delta B is equal to F delta C. Okay? That's something that we're coming up with. And it's hard to do this lab. I mean, Ms. Vaughn and I tried it, and we did a bunch of trials. So we're happy that you can see what happens on the graphs, and then you can see this general trend. So F delta T is equal to M delta B, and that is going to be our formula that we're going to use for this chapter. Now, it'd be kind of nice if we had names for these values, wouldn't it? Yeah. These groups of numbers. So I'm going to give you a couple of names. And this should go in your intro paper that's coming in your binder. It's the thing that you took the notes on to begin with. This first part, exploration, when I introduced it, I asked you to write some things down about it. You probably want to draw into the setup, just information that you might have. Yeah. Okay, so M delta B has a name. And that is change in momentum. I'm going to explain that change in for a second. If I have M times B, I just have the momentum. But if I look at the change in velocity, I have the change in momentum, don't I? Would it be possible to change the mass and get a change in momentum? Think about that. That's kind of down the road a little bit. And Ft is called impulse. So it's fair to say then that we can say change in momentum is equal to impulse. That's our big idea today. Let's think about how that works. If, Jordan, can you help me out there? Push that card across. If its momentum is changed, what provided the change in momentum? The impulse did. Let's say I'm a golfer and I want to apply an impulse to a golf ball sitting on a tee. So here's the golf ball. Can you imagine it right here? And I'm gonna swing and I'm gonna hit the ball, and I'm gonna change the momentum of the ball. It's gonna have a change in velocity, isn't it? What does that? It's the impulse that I apply. So as we think about that, is the impact the same as the impulse? Let's think about hockey example. Okay, help me out here, Sam. I know a lot about hockey. What position you play? Forward. I don't even know what that means. I'm just trying to score a goal, right? Okay. So if you ever body check anybody in hockey? All the time. So if you're going to apply an impulse to somebody, what's the difference between impulse and impact, do you think? Talk about that. Would there be a difference? Impulse and impact.
Do you want to turn your mic on?
I think it is. I think this board is just blocking out. How's the battery?
Red.
Okay. Okay, what do you think? Any thoughts on that? What do you think, Trey?
Impact is actually when you hit something, and then the impulse is when you hit something and then you change its velocity. So if Sam hits the guy, it's changing which way the guy is going.
Okay. So you're saying that he could impact the guy and the guy wouldn't change velocity?
Hit him up against the wall.
Yeah.
Okay. Or even if is this an impact then?
Yeah.
That impact? So let's look at this formula and say, is there a part of this formula that's actually impact? And that might clarify it for a second. What? Yeah, that's true. That's an impulse, isn't it? So when we talk about the force, let's use that. Helio is going to kick a football. He applies a certain force, and that part is called the impact. Just the force. But here's the ball on the tee, let's say. Okay? Like that. And here's his foot. Does his foot contact the ball? Oh man. Oh, that's not bad, is it? See, it's a cleat. No, it's pretty skinny leg. So does his foot impact the ball for a certain amount of time? It does. It takes him a certain amount of time. Do you get a better kick if you push on the ball for a longer time?
Yes,
Follow through. Okay, there we go. So what is happening is that he's applying an impact to create an impulse. All right? And this whole thing is the impulse. It's the force times time. All right, here's what I want you to do. I'd like you to clean up your board, put it back, and then we're going to try a couple of practice problems.